where we, as Julia said, operate a little differently. We have a panel. And before we even go anywhere, I wanted to briefly bring up something related to last week's. And you might remember we had the bottle and you were kind of trying to find out the angle of elevation, and then you entered it all into a form, and actually the winning team, can you see that? Well, I just blind. Okay, the winning team was team 24887, and we kind of promised, and actually, before I do that, they got the angle right within 0.3 of a degree. That's 0.3 of a degree. And you all remember how difficult the experiment was, how it was kind of lots of uncertainties in moving this around. So this is an absolutely remarkable result. And the two people that were that particular team, Melissa and Victoria, and if they're here, they can come up and claim their prize. So here we go. And the prize is one of our wonderful, all-time beautiful neutron shirts. Congratulations. You want to say something?
Yeah, about the rainbow. So
you have like 20 seconds. I'm going to be just like that today.
So, do any of you remember that I gave you a formula of that towards the end of what the rainbow angle really is calculated? Did anybody remember? Yeah, okay. You weren't here. So, there's another t-shirt coming for the person that can send me that formula for 2 rainbows, the second bow, the third bow. I gave it for the first bow, right? So if you can give me the formula for the second or the third bow, another t-shirt, okay? Yes.
So everybody gets the formula right, gets a t-shirt, do you have one t-shirt? Okay. So that brings us to today, and probably all of you are starting to think about the essays you can submit to complete if you will for one of the internships. And since it looks like not all of you have read what's on the website, let me make one remark. It's really a good time now to bring up the rules and everything that's posted on the website in terms of requirements. And the ones I briefly want to mention, you must have attended 4 of the first Science Saturdays. Today counts. If this is your 4th one, you're still fine. The essay is supposed to be 4 to 5 pages long, and it tells you double space and the font size and all these kind of things. And if you actually go to the web link that's given there and you look at it, it gives you kind of an idea of an outline. And it's probably a very good idea if you think of those kind of as your headings, which go along, why did you choose these challenges and things like that. It kind of gives you an idea how to structure that. So, that's a very good start. And today's discussion is really aimed at giving you the opportunity to ask questions about the engineering challenges, maybe get inspired by something that one of our speakers says, and get you some ideas. The deadline is the 24th, which means you have not a lot of time left, not even quite 2 weeks, to get your essay together and send it to the email address that's given there. The other thing I wanted to briefly mention, and I can't read this on the screen, so I'm going to walk over here. You might remember that we sent out a survey which said, which engineering challenges are you interested in? And about 25 of you responded, so that's probably the same response rate as for the survey. And this is kind of, and you could put more than one, so the one that was by far the most selected one was make solar energy economical, directly followed by provide clean access to water, provide energy from fusion, enhance virtual reality, and then you can see the other ones going down. And it's very nice to know that we have experts on solar energy, on clean water, and on fusion on our panel today, in addition to 2 other ones. And so thank you for those who actually went through. There was a question of, if you write the essay about a particular engineering challenge, if that means you need to work in that area, should you get the internship? And the answer is no. Once we have down selected to the number of people that we're going to host over the summer, we're going to make the metrics adventures, we're working on the schedule, we're doing all of this. So don't feel constrained by what you might or might not do in the summer when you select an engineering challenge you want to write about. Write about something you're passionate about, and you might work in that area, you might not, so it doesn't have to be in any way. And since I know Tom has this in his presentation as well, I'm not going to read through all the engineering challenges in the interest of time, but again, if you follow the link on the website, you actually find information and videos on this website that was put together by the National Academy of Engineering. And before I hand over, I want to really thank all the panel members who took a Saturday morning, out of their busy schedules to come here and talk to you. And I think this is a good time to give them a hand of applause for that. Now we did this before they have done any work. So that's usually not kind of what I do, but that's okay. And the other thing, before I hand over to Thom Mason is, and somehow the red really doesn't show up over here, is that we have a wide cross-section of directorates across the lab. We have people from outside the lab. We have the director of the Tennessee Clean Water Network here who's going to talk to us. So don't be shy. When question time comes, ask questions, be interactive, seek out the panel members at the end. Don't let them leave the auditorium asking your questions. This is your opportunity to interact with them. None of them need to go home until like late this afternoon, so you can just keep the right. Okay, and with that, see the microphone's falling off. And with that, I'll hand it over to Thom Mason.
Okay, I was going to talk a little bit about the engineering grand challenges, and I was going to start by giving a historical example of a grand challenge. This is just an excuse really to tell you a little bit of history of Oak Ridge National Lab. But the National Lab, at the time it was initiated, which was in 1943, was called X10. So there were 3 sites in Oak Ridge: Y12, K25, and X10. And its purpose really was to solve an engineering grand challenge associated with the Manhattan Project. So in 1932, James Chadwick had discovered the neutron. He'd been studying radioactive decay, and there had already been some work in this field, so people knew about alpha decay. For example, an alpha particle is basically helium, a helium nucleus. And they knew about beta decay. Beta is an electron. And Chadwick was working in Rutherford's lab in Cambridge, which was kind of the center of the universe for things to do with nuclear science. It was Rutherford who figured out that an atom was made up of a heavy nucleus and a cloud of light electrons around it. And Rutherford figured that out by shooting alpha particles into material. And so this was a pretty hot topic at the time, and Cambridge was the place to be, and that's where Chadwick was. And so he was studying radioactive decay and observed this new decay mode where the particle had some different characteristics to the ones that had been known. It didn't have a charge. That was the really unusual thing about it. The betas and the alphas had charge. Gammas didn't have charge, but they also didn't have a mass because they were photons. So this new thing, which he coined the neutron in a short paper that was published in 1932, was kind of an interesting discovery. And that set off a series of work, mainly in Europe. And so you had people like Fermi in Rome, and in Germany, in Berlin, you had Hahn and Liesmeitner and Frisch, who were studying the properties of this thing. And one of the things that was discovered in Germany and Berlin was that with a neutron you could fission a nucleus. And in particular, they discovered that you could fission U-235, which was one isotope of uranium that occurs naturally at a small fraction of uranium as U-235. And then when you did that, you got 2 neutrons out. So 1 neutron went in, 2 neutrons came out, and that meant you had the possibility to do a chain reaction because you got more neutrons out than you put in. So 1 could go in, 2 could come out, and then those 2 could go and make 2 fissions, and that would turn into 4 neutrons. And so pretty quickly you'd have a whole bunch of fissions going on, and each of them released a relatively large amount of energy. So that all happened in the 30s in pretty quick order after this 1932 discovery of the neutron by Chadwick. And after the paper was published, on the fission of uranium, people began to realize that if you thought for not too long about how much energy released, it was enormous. It was much more energy than was released in a chemical reaction, because the binding in nuclei is much stronger than chemical binding. So when you broke one apart, the energy release was much larger than in a chemical reaction where you might be breaking a chemical bond. If you think of explosives like TNT. Which interestingly was discovered by Nobel, the guy who founded the Nobel Prize. That was his claim to fame. So if you recall your history, at that point in time, the world was headed into a pretty difficult and dangerous period, and people began to get nervous about this because they realized that with that large release of energy, there was the possibility of a new and different type of explosive. And so that led to the famous letter that was sent to the president by Einstein, which if you go, I don't know if you go through the visitor center when you go to the lab, but there's a large blown up picture of this famous letter that Einstein sent. It wasn't actually written by Einstein, it was written by Leo Szilard. And, but they felt like the only way they could get the president's attention was to have the most famous scientist in the world at the time send him the letter. So Szilard went to visit with Einstein. They'd known each other in Europe before they fled. They were both refugees who came to the US. And in that letter, Einstein basically says, because of this discovery of fission, there's the possibility of a new and tremendously powerful type of weapon. The science is pretty clear. In fact, all of the work had been done in Europe, so it was pretty clear that if Germany set out to try and exploit that, they had a pretty good chance of figuring it out, given that even though they lost a lot of great scientists who came to the US and the UK, there were an awful lot of good physicists and chemists and engineers who stayed behind, and so Einstein said, we better look into this, and that was what started off the Manhattan Project. So the physics of the bomb was actually not that difficult to figure out once you knew that uranium would fission. You had to have enough U-235, that's what's this thing called the critical mass is, and if you could get enough U-235, then you had the possibility to make a what was at the time called an atomic bomb. Now, the science continued, and it was found that there was another fissile nucleus that might be a good candidate, and that was plutonium, plutonium-239. Plutonium is actually an artificial material. It doesn't occur in nature the way that U-235 does, but it was possible to manufacture it in very, very minute quantities using the cyclotron at Berkeley, which was an accelerator. And so people at Berkeley had made very, very tiny quantities of it, observed that it was fissionable. So there were kind of two candidates for how you could make this bomb. You could get U-235, and the challenge there, the engineering grand challenge there, was how to purify U-235, which is a tiny fraction of natural uranium. That's less than 1%, it's 0.7%. And you have to purify it to a much higher percentage. That's called enrichment. And so you read in the newspapers about how people are nervous about Iran and North Korea and what they're doing. One of the things they're doing that has people nervous is they're enriching uranium. And so that was a challenge, but if you could get enough U-235 to make that critical mass, you could make an atomic bomb. With plutonium-239, it was a little bit different challenge. Plutonium-239 doesn't occur naturally, and the way that it was being made was to take U-238, which is the most common form of uranium in nature. That's when if you find uranium ore, it's almost all U-238, and you hit it with a neutron, and when it absorbs a neutron, it becomes plutonium-239, and that's fissile. So the challenge there was, okay, if you can irradiate with neutrons, then you can make this plutonium-239, which you can chemically extract from uranium because it's a different element. It's got a different spot in the periodic table, so the chemistry is different, so you can use chemistry to separate it, which you can't do when you're enriching uranium. So if you had enough of those, either of those materials, you could make a bomb. Now, there was a lot of engineering and physics that went into the details of making the bomb, but the job for X-10 was associated primarily with the grand challenge of getting the plutonium. And so you see in this picture here, I guess this laser is not terribly powerful.
Use the mouse.
There's another engineering grand challenge called green lasers, but
use the mouse. Use the mouse.
You can use the mouse.
Use the mouse.
Yeah, so up here you see an aerial photograph of X-10, which became ORNL. And sitting in the center of that picture is something called the Clinton pile. It's also known as the graphite reactor. It's the face of the reactor. And then beside it is a complex that was a chemical processing facility. And the purpose of this facility was to really, demonstrate the feasibility and solve the problems of what's called scale-up of producing plutonium-239 at a massive scale that was required as part of the Manhattan Project crash effort. So plutonium-239 had been manufactured in minute quantities, micrograms, at Berkeley, and so it's hard to do chemistry with micrograms, but you know that people like Glenn Seaborg who were pretty good at chemistry. So they had an idea, and they knew where it was on the periodic table. And of course, once you know where something is on the periodic table, you know how many electrons and you know, that sort of thing. You can start to do the chemistry in your head, even if you don't have the material. So they had some ideas about how this was going to work, but in order to test those ideas, they needed more than micrograms. They needed probably grams. And if they were going to really build an industrial complex, if you're a chemical engineer, the thing you learn is that scale-up is the big challenge. The famous story about scale-up, and I don't know if this is true, but I think it's taught to chemical engineers, at least that's what my brother told me, is Kevlar. So most of you are probably familiar with Kevlar. It's made by DuPont, big chemical company. It's a very successful product. It's used in tires, radial tires. It's used in canoes. It's used in body armor. So it's got great properties. And it's actually a product which, even though it's very successful, will likely never pay for the investment that was made to turn it into a product, because it costs so much to figure out how to go from being able to make it at test tube scale to being able to make it at industrial scale, that the revenue associated with producing it from now till infinity will never pay back the interest on the capital investment on scale-up. So that scale-up is a big challenge for chemical engineers. You do you work with test tubes and beakers. You can show I can go from this and this, put them together, cook them in this way, something else comes out. That's great. That doesn't tell you you're ever going to make any money with a product, because it's a question of how can I do that at the ton scale or the thousands of tons, and how much is it going to cost, what's the plant look like, how reliably is it going to operate. And so typically, before you commit to a big industrial scale activity, you want to do something like intermediate scale. It's called a pilot plant, or a semi-works was one of the things. And this facility here was called the semi-works for a facility that was ultimately built in Hanford, because it had the reactor that was going to do the neutron irradiation of U-238 to convert it into plutonium-239. This is the graphite reactor. This is like a mini version of the Hanford reactors. It's the first continuously operated nuclear reactor. Fermi, after he left Europe, came to the US, he was at the University of Chicago. He demonstrated the reactor concept at something called the Chicago pile, CP1. The reason they called it a pile is it was a pile. They stacked up blocks of graphite and uranium until they had enough that it could sustain the chain reaction. The first real engineered reactor, which was actually built by DuPont, the same company that did Kevlar, was built in Oak Ridge, and this was a real design structure. You can go and see it. It's a National Historic Site. It was built in 9 months, remarkably, And so that was going to make plutonium in quantities that hadn't been available with the accelerators that they had. And then this chemical facility beside it was going to do the chemical extraction. So that was the semi-works or the pilot plant for the chemical processing facility. So that was an engineering grand challenge. The chemistry had sort of been worked out. The physics of the nuclear reaction had been worked out. But they've been done in kind of a research mode, and now you have to turn this into something that works. And you know, that's my definition of an engineering grand challenge. It was tremendously important as part of the war effort. It was extraordinarily difficult, and it was trying to take something that had been worked out scientifically, but had not yet been proven to be practical. So that's going to be my working definition of an engineering grand challenge, and I think it's consistent with the National Academy's definition. And actually, as a result of that, and that success, that was what led to the creation of the national labs. Picture here is President Truman signing the Atomic Energy Act on August 1st, 1946, after the war. And the idea was to capitalize on the extraordinary scientific and technical capabilities that had been brought together for the war effort, continue developing this new field of nuclear, and do fundamental research using these tools, the reactors and accelerators and that sort of thing that I talked about. So Oak Ridge is the department's largest science and energy lab. We do a wide range of things, and actually many of them relate to the engineering grand challenges. So I'll go through that a little bit. Certainly, as a Department of Energy lab, one of the things we worry about is energy. It's really central to a lot of the compelling issues that we face as a society. The environmental impacts of energy production, distribution, and use, emissions, CO2 and other emissions, national security and global security implications of energy scarcity. We see a lot of conflict in the world around things related to energy, whether it's instability in the Middle East or standoffs between North Korea and South Korea. You know, it's all tangled up with energy. Then there's the economic consequences of energy prices, and sometimes that's something that's a little bit harder to see because everything we buy has energy priced into it. So for example, there's a strong dependence of food prices on energy prices because of the energy used in agriculture and in the distribution of food. So when oil prices go up, food prices go up, and that can lead to instability. You know, one of the countries that people are very concerned about right now in terms of stability is Egypt. You know, part of the instability there is political instability, but a big part of the instability in Egypt is driven by food prices. 40% of the average family income goes into purchasing food in Egypt, 40%. And it's strongly dependent on energy prices, and Egypt only produces enough food domestically to meet about 1/3 of its needs, so it's totally dependent on foreign aid, actually, to purchase that food. So it's a very unstable situation, and there's an energy component to it underneath the surface. And finally, energy access in developing nations. Our standard of living is basically defined by the amount of energy we have access to. Roughly speaking, if you look at the average energy use in North America or Western Europe or Japan in the developed world, we use the energy equivalent of 100 servants for every man, woman, and child in the U.S. And what do I mean by that? Well, we know how much energy we use per, gigajoules per year. It's 250 gigajoules per year per person in the U.S. And if you work it out, an individual human requires about 2,000 calories, maybe a little bit less if you're dieting, a little bit more if you're not, per day, just to keep you alive. So that's the energy equivalent of a human, and you can take those calories and do work with it. And traditionally, before the beginning of the Industrial Revolution, you might use animals instead of people, but it's roughly the same sort of equation. That's why we measure power and horsepower, actually. And so if you look at our energy consumption in the U.S., as I said, for every man, woman, and child, it's the equivalent of 100 people of effort. Now, what those, quote, energy servants are doing for us is they're lighting our lights, they're heating our houses, they're moving us from place to place. And if you think of that average family of 4 then, with the equivalent of 400 energy servants, if you look back in the pre-industrial age and say, you know, what fraction of the world's population had 400 servants for their family? You know, that was a pretty select group. You'd have to be some kind of feudal lord or something, and not just a little mini feudal lord. You'd have to have a pretty good, you know, chunk of the planet that you had control over to have 400 servants at your disposal. And that's what the average family in the US has access today because of our energy use. Conversely, if you're in the developing world, that's what you don't have access to. And so that's why energy access in developing nations is such a big deal, because that's standard of living. It's light at night so that you can read. It's food or fuel so you can cook your food, and fuel so that you can grow and transport your food. It's transportation. It's communications. It's, you know, freedom from cold and disease. Whole set of things. So energy access in developing nations. So energy is full of grand challenge, and that's why our programs actually address in one way or another most of the engineering grand challenges. So I don't have a lot of time to go through all of these, but what I will do is just take a bit of a random selection, and then maybe I'll take a few questions, and so you can point me at some. And so let's see, I'll just, since we had the popularity contest on this, I'll maybe start with the ones that attracted the most interest, and then see if there are questions on others. So I think the number one choice was making solar energy economical. And it's interesting, just this year, it looks like we're going to cross over the point where globally we're going to get more energy out of solar than we put into it. It's kind of a, you know, this is what we mean actually when we say solar hasn't been economical. Until this year, the amount of energy that was consumed in making a solar cell, the total energy, you know, to get the silicon, to purify it, to you know, make the structure that holds it, to move it to where you're going to put it in. The total energy that you put in was more than you got out until this year. Now the production has been ramping up. The energy per cell has been put in, has been going down. In other words, the price has been going down. And so this is the first year where the total global output will exceed, integrated over time, will exceed the energy input integrated over time. But that just means we've kind of hit some kind of break-even point. It still doesn't mean that solar is competitive with other forms of energy in terms of cost. So in order to reduce cost, there are a couple things that you want to work on. Improving efficiency will help. So you'd like to work with lower cost materials that have the right properties. And it's not just about photovoltaic. There are also ways to access solar through fuel production, and so you'd like catalysts that would allow you to convert sunlight into chemical fuel, so that you have access to not just electricity, but some kind of portable fuel. There are novel methods for self-assembly of molecules into functional systems. This is another way to get cost. If you come up with some, you know, really brilliant, sophisticated, high-efficiency, extraordinarily complicated to manufacture technology, it's probably not going to meet your cost target. If you can somehow trick nature into doing some of the work itself, it might. There are new designs for high-efficiency solar cells, and there's lots of materials issue for converting solar energy into some grid-compatible electricity. So this is something that we have lots of different pieces in, mainly because of the materials R&D that we do at the lab. This is an example of one trying to essentially take advantage of some of the tricks of nature, nano-fermentation to produce photovoltaic materials. These are microbes that people were studying because they thought they might be useful for cleaning up uranium in the soil, which is one of the contamination issues that we have to worry about here for going back to the Manhattan Project. And it turned out that these bugs, these microbes, if you fed them the right chemicals, and then instead of kind of concentrating uranium and extracting it, they would basically poop out nanoparticles of a really good photovoltaic. And so this was kind of a very efficient way to make kind of control nanoparticles. And then, so that's maybe the science. There's an engineering grand challenge in how to take that and turn it into something that's useful. So lots of different aspects of that. Next one, provide energy from fusion. This is a big effort for us because Oak Ridge is responsible for the U.S. contribution to something called ITER. This is a cartoon of what ITER is supposed to look like. There's a person standing here. So that gives you an idea of scale. And what this is an extraordinarily large and complicated superconducting magnet that produces a magnetic field that combines something called plasma, which is basically a cloud of very hot charged particles. And that plasma is intended to have sufficient temperature and density that it can sustain a fusion reaction, which is the way that the sun produces power. In fact, arguably, pretty much every form of energy we have is some form of fusion power. Nuclear power comes from, our nuclear electricity comes from uranium, which is produced in an exploding supernova, so that came from fusion. The sunlight that we use for not only photovoltaic and other forms of solar energy, but plants, so trees that we might burn in the form of wood, or oil, which was previously sunlight that turned into plants and dinosaurs and got crunched into oil. So basically, everything we've got goes back to fusion energy from the sun, and this is just an effort to do that in a controlled way on the surface of the planet. And so there's issues of understanding through computational tools how this works, but there's also the very practical thing of, how do you build this thing? What are the materials that you're going to use that are going to survive in this incredibly hostile environment where you've got this plasma and high magnetic fields, you've got lots of energy, meaning things are going to be hot. You've got to deal with the tritium that you need to sustain reactions. So it's a very rich problem that's requiring not just actually the U.S., but in fact a global partnership. The U.S., where we have to lead for that piece, China, Russia, the European Union. It's being built in France and Cadarache, South Korea, India. So it's over 60% of the world's population that's paying for this through their taxes, basically. So that's another grand challenge. I'll talk maybe about one more, and then see if there are any questions. And maybe I'll say a little bit about this one, since one of the things the lab does is operate big tools in pursuit of science. And most of these are represented in our user facilities, and there's a list of them here. So we have things like our supercomputer Titan, spallation neutron source, the high flux isotope reactor, or Center for Nanophase Materials Science. So these are wonderful scientific tools. You've also got to build them, and it turns out that is an engineering grand challenge in the same sort of spirit that the graphite reactor and the processing complex was, and it requires all kinds of different engineering skills: electrical engineers, mechanical engineers, computer science and engineering for the software side and controls and so forth. And that's really one of the special roles of the national labs is building and operating these major facilities, and every one of them tries to push the envelope of the possible in some way. So I think at that point I better stop because I'm probably over time. But if there's any specific questions that people have about any of these, I'd be glad to improvise. Yeah?
I'm curious on the secure cyberspace. What does that exactly entail?
Well, this is, oops, well that's interesting. It doesn't have anything to do with nanofermentation.
It's very secure.
This is a good example.
That's it showing.
If you just
Maybe
step through them, you might.
Yeah, that'll need it. So, actually, you may not realize it, but there's a pretty substantial global conflict going on right now in cyberspace. For example, the largest U.S. financial institutions for almost the last year have been under pretty much constant attack. So big banks like Chase, Citibank, and in fact, their websites have been brought to a stop for various periods of time. And the reason that's happening is that what used to be a kind of unsophisticated attack called denial of service. So denial of service attack is just where you bombard a website with requests. You just get a whole bunch of different computers to try and simultaneously load web pages. And if you get enough of those, then the whole thing grinds to a halt because it just gets gummed up. It can't respond. So the traditional way that denial of service attacks would work would be that there would be some activist group that would have a botnet, a collection of maybe 1,000 compromised home computers because, at home we're maybe a little less careful about cybersecurity, and so we get some malware on our computer, and that would give control to some organization, and they get 1,000 computers to go after a website. And that's a problem if you've got a small website, but if you're a big bank, you can probably ride through that. That's not what's happening now. What's happened is somebody has compromised some big servers in data centers. And they're powerful, and they have really high network bandwidth. So they can generate a huge number of web page requests. And so this is not just some sort of botnet of thousands of home computers with kind of low bandwidth cable modem connections. These are big data centers that have been compromised. They have huge computational power, huge network bandwidth, and they are powerful enough to really go after these banks. So, someone has decided they want to go after the U.S. banking system, and it's been going on for months. So that's one example. And it's been widely speculated in the press that this has its origin in the conflict that's going on in the Middle East right now with Syria and showdown with Iran and so forth. Another example is, this is something that happened, I think, around last August. There's a company called Saudi Aramco, which is the Saudi oil company. It's responsible for a reasonable fraction of the world's oil supply, which, in fact, a large enough fraction of the world's oil supply that if it were to stop, it would probably create a global financial crisis because the oil prices would shoot up dramatically. And 30,000 of their corporate computers were basically destroyed. The hard drives were erased, and all that was left on them was an image of a burning U.S. flag. And none of the systems that control the oil distribution and production were compromised because they were on a separate network. So this was tremendously damaging to Saudi Aramco. Pick any company and destroy half their desktop computers, and you've done a lot of damage. I can't imagine what would happen in ORNL if half our desktop computers got wiped. I'm sure everyone on the panel is diligent about backing up their work, but we definitely lose a lot of time and money. But probably the real target with Saudi Aramco was trying to disrupt the production, because that would have really got the world's attention. Because this didn't disrupt production, it didn't get so much attention. It was on like page 15 in the New York Times or something, and people didn't really notice it. But that was kind of a big deal. So there are starting to be lots of examples of things that are happening that have not yet, risen to the level of major damage or disruption, but they're starting to get uncomfortably close. And of course, they're facilitated by the fact we have this tremendous ability to communicate. Ubiquitous network access, ubiquitous use of computers to control things, whether it's the electric grid or the banking system or the production and distribution of oil. And when you combine those things, control of things that are critical to the functioning of society with ubiquitous network access, it's kind of like not to be too alarming, but it's kind of like figuring out that you can fission U-235. And so people have figured out that they could fission U-235. And now they're trying to scale that up. And so the grand challenge is, how can you stay ahead of that curve? And this is a problem of certainly software design and software engineering. It's also a social problem. Human behavior. We love to take advantage of all of this and Facebook and email and all that sort of stuff. And actually almost all of these attacks at some point in the chain take advantage of human weakness, because that's easier to get around often than the engineered protection. If you can just convince people to click on something in an email, then 90% of your job is done. So it's not just computer science and engineering, it's also a social engineering, if you will, problem. You see it also in North Korea and South Korea. There's been a lot of attacks in South Korea to the things that make the South Korean economy function that are almost certainly coming from North Korea. So it's a big challenge, and it's not going to go away. Other questions? Yeah?
Yeah, I just wanted to comment on that because I read an interview recently. It was an anonymous interview done by one of the world's premier hackers. He gave an alias. But basically, he said that he has a botnet of over 400,000, home computers with, like you were saying, high bandwidth. And, he doesn't do this, he doesn't, he will attack networks, he'll attack banks, and he'll make a lot of money off of it selling user data and selling credit card numbers, but this is just a hobby of his. And so what a lot of experts I've read are talking about is that, a lot of the people who have the capability to cripple our infrastructure, the only thing that's keeping them from doing that is that they're really not interested in causing mayhem. They're just wanting to have fun. And so we actually see people who are interested in cyber terrorism. If they start developing these capabilities, we really have no defense.
Yeah, so that's true. The most visible stuff has been kind of people who are either motivated just because you can, and it's tricky and challenging and interesting, or people going after credit card information for fraud and so forth. If that's all it was, it would be probably more manageable. It's that last step that you mentioned that is scarier, because now you're talking about the resources of nation states. The thing that's been happening over the last couple of years is we are now seeing that happen. So that's not just a, what if people interested, that's what Saudi Aramco was. Now, if you look, there's oftentimes efforts to make it appear like it may be just kind of an uncoordinated hacktivism thing, but those don't typically stand up to scrutiny. And that's why, for example, the denial of service attacks on the banks that are going after data centers, those are much more sophisticated than are likely to be mounted by, a clever, obsessed individual in someone's basement. Okay.
I'm going to move this along. There will be more opportunities to ask Thom questions as he is on the panel. So if I can invite the panel members to take a seat, they will change the name. So what we're going to do is moving on. Every of the panel members will have just a brief moment to say who they are, what they're doing, and address, one or two of the grand challenges that are within kind of, the scope of their work. And then we hope to have still, half an hour left, and you can ask questions, and we either pick the expert, or if there's no, or we default to Thom if it's a question nobody else can answer. So that's kind of the idea. And I mean, we could just take it in order and start with Andrew. And so I kind of, he has a few slides to show and tickle this about. Great.
Okay, so Thomas asked me to talk just briefly on engineering the tools of scientific discovery. So my name is Andrew Pazan. I am kind of one of these weird crosses of an engineer and a scientist. I sort of, I guess, cross both. If I do that? Yes. So a lot of you, I'm sure, watched The Big Bang Theory. And Sheldon's quote from The Big Bang Theory when he walks into the room of engineers, if you've seen the show, he says, where the noble semi-skilled laborers execute the vision of those who think and dream. I'd like to think engineers are a little more than the Oompa Loompas of science. So
we could take the pump down, we'll take.
Yeah, well, let's not do that. If you look at the Grand Challenges website, the National Academy of Engineers basically have summarized it this way. They say, grand experiments and missions of exploration always need engineering expertise to design the tools, instruments, and systems that make it possible to acquire new knowledge about the physical and biological worlds. And that really summarizes what Dr. Mason talked about earlier. There were two topics highlighted in there, and I'll just go through those quickly. One question was, how would engineering impact biological research? So they highlighted new kinds of microscopes, new biochemical methods of probing the body's cellular and molecular machinations, new mathematical and computing methods, now you get into computer methods, and new methods for studying the brain. What sort of things are we talking about here? This is what already exists. Excuse me, what already exists. Things like this, the CT scanner, PET scanners, DNA sequencers, and of course the supercomputers that enable a lot of the advanced modeling and simulation that we have today. Another question they raised is, how will engineering help us explore the universe? So long-distance human spaceflight is a big challenge. So far we've had human beings on the moon, and most of you participants in the audience weren't born the last time somebody walked on the moon. So you have many obstacles, dangers of radiation in space. How do you supply sufficient food, water, and oxygen to maintain your explorers? So we also have issues with new and improved telescopes, both ground and in space. New devices to measure things for astrophysics, gravity waves, for example, or neutrinos. And again, here's some of the things that exist today, thanks to the partnership of science and engineering. The Curiosity Mars rover, which you see up in the corner, that's an amazing engineering accomplishment that enables us to do science on the surface of the moon. And if you haven't gone to the NASA website and seen what they're doing, I highly recommend that. The Hubble Space Telescope and the International Space Station are other aspects of that I think you probably know quite a bit about. So those are some highlights. I don't want to take much time. The big question here is how can you contribute? Engineering has the possibility here to change society. So that's what I have to say.
So I'm going to just move this through the panel and do the question at the end. So that there's a microphone if you want to.
I have a website that I want to pull up. Okay, so my name is Lauren Descartes, and I work in Oak Ridge National Lab, and I develop new microscopes, so that fits exactly into what was just discussed right now. And I just wanted to pull up a website as a resource if you're interested in writing this kind of subject on
maybe not the word.
Sorry. And so, do you guys know about nanotechnologies, and do you know where you can find nanotechnologies in your everyday life? So if you look at your computers, your phone, for people who wear sunscreen or makeup, or even your shampoo, everything that is around you every day is impacted by nanotechnology today. And a great need now is to be able to look at that scale. So we need new microscopes and new ways to approach the cell and understand how they work to develop new medicine or understand how diseases develop. So that's the kind of things that I've been focusing on, and that I'll be happy to answer your questions if you have any.
Good morning, my name is Renee Oyos. I'm the Executive Director of the Tennessee Clean Water Network. I'm the only one on the panel that's not from the lab, so how many here are familiar with hydrofracking as a means to extract natural gas? How about anybody here see the documentary film Gasland? A couple hands, yeah. Okay, I was going to take you through this video to show you how hydrofracking works. As Mr. Mason mentioned, energy is a big, it's an issue that we're all grappling with. We would like to have energy independence, and yet some of these energy extraction methods can be harmful to water quality. You know, this is a long video, so I'm actually just gonna not go through all the different phases, except to say that our organization is mostly a policy shop. We don't do a lot of engineering, but engineering and policy do intersect in that engineering can create guidelines and processes that can do things like protect water quality. And yet, our decision-making bodies, like state legislatures and state agencies, often don't trust engineering. And so, I'm going to tell you a really quick story and then I'll sit down. About a year ago, the Tennessee Department of Environment and Conservation was opening up their oil and gas regulations. And there was nothing in there on hydrofracking. And that means that anybody doing hydrofracking would be subject to no regulation, except the very basic oil and gas regulations. And so a bunch of us got together and we looked at the American Petroleum Institute standards, which are engineering standards created by the oil and gas industry's own experts. And we put that into regulatory language and we offered that to the state. Had lots of controls on casing standards, lots of controls for protecting water quality. And the state actually did not accept any of our suggestions, which were industry suggestions. And so along with these grand challenges, and you also have to remember that there's an implementation phase, and that is as important as creating these great technologies that protect water and air quality.
And we can email this link to people. So
oh yes.
This, because it's kind of a complicated thing to remember. We can set that up.
Yeah. Yeah.
How many of you came by just walking or biking or by a car today to this event? All of you. And no one chose that as a challenge, the engineering challenge we face today. And my name is Rekha Pillai, and I work at Oak Ridge National Lab, and I was asked by Thomas to talk about an important infrastructure and the engineering challenges we face in that arena, and that's the transportation system. So transportation system constitutes many different components, not just the cars or the vehicles or the conveyance that we use, but also the infrastructure itself in terms of the roads or the bridges, the tunnels, you know, the different the ports or the interchanges and things like that, as well as how we operate it, how we maintain it. And right now, what's the problem with it is that that it is getting extremely old. It was designed by our parents, our grandparents, and we are moving ahead and we want to try and it is also stressed because of the increases in the growing population and the growing urbanization, and also it's decreasing our quality of life through, you know, major contribution to pollution and greenhouse gases. And it's impacting our quality of life, and we have to also face major challenges in terms of giving access to not just you know, the I mean, we have to increase the access to disabled, to people who are living in the rural communities, and to a larger portion of the population. It's at risk right now in terms of terrorist attack or changes because of climate change and those kinds of things. So that's why we need to not just upgrade our current infrastructure, but also figure out how to build new infrastructure. And if you think about just looking at your house and reconstructing that or breaking it down and putting new homes, how would you do it? This is at a much bigger, grander, broader scale that we are talking about to improve our mobility. This is important because this is what provides us the economic growth, the competitive advantage, provides us the personal freedom, allows us to grow, remain competitive globally. This is what also is a major driver of the globalization. And so it's an important component. How are we going to upgrade it? What are the ways we can design new things? What are the ways we can integrate so that mobility, efficiency, reduction of emissions that is improving our way of life, and increasing our security and safety. These are all important aspects. So this is one of the challenges that we face, and I've provided some approaches that we are undertaken at Cooperation National Lab, but this is not the only, these are not the only components that we can work on. Thank you.
I'm Bobby Whitten. I work with supercomputers out at the lab, so I work with the DOE supercomputers, I work with the NSF supercomputers, I also work with some NOVA supercomputers we have out there. Supercomputers are the tools we can use to answer a lot of these grand engineering challenges that we've been talking about. You can use supercomputers to simulate fusion energy, you can simulate poop that comes out of bacteria to give us photovoltaic cells. Anything you can do in an experimental facility, you can do on a supercomputer. A lot of times supercomputers are cheaper. You can do things you just can't do in the real world. So there's a lot of grand challenges that can be aided with the tool of supercomputers. Now, one of my grand challenges when I talk about supercomputers and people using those supercomputers is how do they make the most efficient use out of the supercomputers. So there's really a grand challenge of educating people about supercomputing. There's a grand challenge in general of teaching people how to use computers to get things done. And in the case of the laboratory and the research we do out there, it's getting people to understand you can use computers to understand science and do your research using computers. Now, most people understand what the most important thing with a computer is to be able to update your Facebook page. But computers can actually do a lot more than that, and people need to learn, and part of my grand challenge is helping people learn and train them and educate them that you can bend computers to your will. Not only are there an information appliance that you can check Facebook and find out what Grumpy Cat is up to today, you can do other more meaningful things. You can do a lot of these grand engineering challenges on a computer first before you try and do it in an actual experimental facility. And that's what I do.
Thank you. So Thom Mason, I am Parantaman, I work at Cooperation National Lab. So Thom already made my life easier about the solar, but I have some new graphs I'm going to just show you. So these are some of the latest work. So I would recommend an article like Steve Chu, our outgoing Energy Secretary, and Arun Majumdar, the ARPA director, and they wrote an article in Nature, August 2012. So this talks about the energy, sustainable energy future. So this is projections from the US Energy Information Administration. So they did this thing for producing electricity from various sources. So I just want to compare where we stand with respect to solar compared to other sources. So these are projections for 2016. So you can see very clearly, so there is a plot of levelized cost of, I'll explain in the next view graph, $ per megawatt hour. So if you really look at, so in converting these, some of these to current production cost is, wind energy, we can make electricity right now 5 to 10 cents per kilowatt hour. So we are very lucky because of the location, Tennessee Valley Authority. We are paying only 8 to 9 cents per kilowatt hour for paying our home electricity. So the nuclear and geothermal are like 8 to 15 cents per kilowatt hour, whereas solar is a little more expensive. So we are in the range of 12 to 18 cents per kilowatt hour. The solar two kinds. So you can convert either light to electricity or heat to electricity. So both solar thermal and both are important for us. And compared to like, as you can see in the plot, bio or hydro or offshore wind or nuclear, still this solar PV and the solar thermal are a little more expensive. So the idea is to have lower cost and also high efficiency. So these are some of the challenges we have. So I'll show you some of them. So let's see the solar market share. So like Thom said, the silicon is dominating the solar market. So we are like almost 90%. So the crystalline silicon is like 85% efficiency. The market share, polycrystalline is 5%. So the thin film solar cells like telluride and thin film copper, indium, gallium, sulfide, selenites. So these are like 10%. So the key problem we have is organic solar cells are still low, 1 to 2%. So the research scale, when you do it at lab scale, these efficiencies we can achieve higher efficiency. Like silicon, we can have 25%, whereas commercial, it's only 18%. So we have a huge gap. So if you look at, for one example I'm highlighting, in the lab scale 20%, whereas the economic, in the commercial scale only 12 to 14%. So we have a great engineering challenge for us to take it from small scale to manufacturing or into a cell and a module. So the major issues are the solar cells are still expensive and there is a big gap between commercial and research solar cells. So the main problem we face is the defects, impurities in the solar cell thing, because you are using light or heat to produce these electron hole pairs. Once you have defects, these electron holes are going to combine and reduce your efficiency. They are really killers. So what we need is the solution. What we have is, or in the Department of Energy, is multi-junction solar cells. All the efficiencies I reported are single-junction solar cells, one cell, like PN junction. If you have multi-junction solar cells and with an efficiency of 40%, maybe you can have. So this is a view graph from Dr. Ramesh, who is going to join our lab as a deputy lab director. He was the director of Sunshot program of the solar and the technology program. So as you can see, just like what we had the moonshot program, we have a sunshot. So this is $1 per watt. So this is a goal for producing electricity for $1. This dollar includes not just a module, it also includes the installation balance of systems and also the power electronics. Because what we produce out of solar cells are only DC. So we need to convert DC to AC, AC to DC converters. So we need power electronics, installation and solar cells. The whole thing is dollar. So as you can see, the manufacturing cost and the efficiency. So if we increase the efficiency, the price is going to come down. Again, we have to have low manufacturing and the efficiency is directly proportional to current density, open circuit voltage and fill factor. These are the three parameters you will measure in a typical solar cell. And you can see here, like all these green are the theoretical limits, the orange ones are the lab scale, and the manufacturing efficiency compared to all these different materials still low. So that's why we still need to do a lot of work. So the balancer system and the utility scale. So the projections are from $2 to $3 per watt to $1 per watt, maybe within the next 5 to 6 years. So that's the goal for the Department of Energy, and we need to work on these different materials. So the other thing I didn't point out is some of the materials like cadmium is really poisonous, and in fact Europe is banning all those cadmium containing solar cells. So we need environmentally friendly material, abundant materials for solar cells.
Hi, my name is Steffi Deem. I work at ORNL and I work in the fusion energy area. And Thom mentioned a little bit of introduction on fusion. So what we do is we work on confining plasma, and plasma is around, it's high temperature, so it's around 100 million Kelvin. So as you can imagine, it's very hot, and it's very hard to contain. So what we do is we use magnets to confine the plasma, and it's almost as if you're confining Jell-O with rubber bands. So as you mentioned, it's very difficult. So we use high magnetic fields, and one of the grand engineering challenges for this is we use superconducting magnets to create the magnetic fields to confine the plasma. We also use frozen hydrogen isotope fuel pellets to fuel the plasma, and also cryo pumps for high vacuum conditions. One of the areas that I work on is heating the plasma and driving current. So what I do is I help design antennas that can actually couple to the plasma instead of injecting energy and having it bounce back out of the plasma. And also we work on optimizing waveguides so that you can get the most efficient energy out of the microwave system. Another area I work on is radio frequency microwave injection into the plasma. So what I do is I do a lot of modeling. I optimize the position of the antenna, and also what frequency can we use to optimize the heating and current drive at the same time. And there's actually a lot more grand engineering challenges. And so you may be wondering, why do we go through this whole process of figuring out these engineering challenges? And the reason why is because the fuel for fusion is abundant. You can find it in water, actually. And to provide enough power for one person for 30 years, you can find the fuel in a half tub of water, and also the lithium battery of your laptop. So that's very efficient and very useful for the US and all around the world.
So let's thank our engineering panel and Thom for what they have told us so far. Not as badly behind as I thought we might be, so I'm proud of myself too. So at this point, I open it up to question. I know some of you have submitted questions, so we're running out of things. I can bring up that list and ask them, but I think I first wanted to give everybody an opportunity to address any of the panel members of any question you want. So who wants to go first to break the ice?
I have a question about what's allowed in terms of paper. For instance, what's the title page have to be?
Okay. So if you go to the website and you look at it, there's a form on the title page where you just say I was at these sessions, you put in your name. And then there's some headings on the next page that give you some idea of what to write. And then it's 45 pages. We can discuss this more online if you have specific questions.
I have one other question about what's allowed.
Okay.
Is it okay if we address multiple issues and some of them we're addressing with different strategies?
Okay, what about policy people? I just say yes. If you have a problem to society you want to address, and you need two of the engineering challenges to do that, I see no reason why you can't do that. Now the question hasn't come up, so I'm making this up. If anybody says this is utterly wrong, who knows about the rules, will rock me down. So I think that's fine. Okay.
Can you propose multiple solutions and talk about a way to figure out which one works best?
Could you give a propose multiple solutions? There we go. Let's have Thom take it.
Okay, does that work? I gave the example of the Manhattan Project as a historical example of a grand challenge. And if you look at that, they weren't exactly sure what the best way to make the material was, so they pursued multiple options in parallel. So for example, for uranium enrichment, they had calutrons and gaseous diffusion and thermal diffusion. And they probably would not have been successful if they just tried one thing. They had to pursue a couple, and then at some point they decided, they said, this is what's working. So I think that's a great approach to some of these grand challenges. If we knew for sure which solution was going to work, it wouldn't be a grand challenge.
Maybe I can answer one. So the other thing, we have supercomputer. So what we want to do is focus on modeling and simulation. So you can always do like combinatorial synthesis. Let's say you want to compare materials with certain properties. So depending on the known materials, so just like Thom said, you can project what we can do, mix of all the periodic table with the known elements. So that's another solution you can do.
Just to go back to the previous question, that is, can you address more than one area together? And that's exactly what the urban infrastructure challenge, it's not one simple solution. You have to address the energy challenge there, you have to address the transportation challenge, you have to address the building challenge, so you can address more than a water challenge. You name it, you have to address, and how you build new communities. So there are so many challenges that are brought together in taking that one challenge, or developing a solution set. So yes, I think that should be okay.
I have a question regarding fusion. I understand that the big challenge there right now is that even though fusion itself produces quite amount, at least theoretically produces a large amount of energy, the magnetic containment fields that you mentioned require more energy to run, and so right now it's not really feasible as a energy source for an infrastructure. What is that ratio right now? Like, how much energy does it cost to get energy from fusion?
So several machines are, can you hear me? Okay. So several machines have actually achieved break even. So that means the same amount of energy that we put into the device, we get the same amount out. And there was a device in Princeton that did that, also over in England called JET. And I forgot to mention this, but there's an exciting experiment that's going to come online, ITER. It's going to come online in a little over 2020. And that means you can actually get involved with this experiment. And this is going to be the first time that there's a fusion experiment where we're actually going to get more power out than we put in. So about 5 times out, 10 times out than we actually put in.
I have a question about that. I have a question.
Okay.
How do you know you're going to get more?
We measure. You mean, what do you mean? Like how
How
do
do
you
you know definitively that you're going to get a significant gain in power?
Well, we can measure how much power we put in with the heating system, with the superconducting magnets, and then we have a lot of diagnostics that can measure how much heat comes out. Does that answer your question?
I thought you haven't done it yet, though.
Right, we've done break-even in a couple devices around the world, which means the same amount of power we put in, we get the same amount out, and we're building ITER, which will actually get more power out. And that will come online in 2020.
So you mold the computer out like that?
A lot of modeling work has been
Right, the modeling.
They think they get more energy out.
Yeah.
They will not really definitely know.
Well, they haven't run the experiment yet, but
So
the modeling.
That's the point.
Right.
They simulate the reaction.
Yeah, sorry.
They're pretty sure, I guess.
Right.
So in a way, they've already done it. They've just done the simulation on the computer. Now it's to see if it actually happens in the real world. And that's what 2020 is.
Because that's another question there.
What's different about ITER that will make it so much more efficient than all the rest?
There's a lot more power going into it. It's a lot larger experiment, so we can actually test. We have more power that we can actually confine the plasma, heat the plasma, optimize the plasma. It's the first time we have all these, this capability.
My question has to do with the security in cyberspace. You're always going to have malicious code on the internet, by definition. I mean, it's like in the real world, you're always going to have crime. How would you then secure cyberspace if you're always going to have malicious code and computers being taken over?
Of course, that's why it's a grand challenge, but the part of the challenge is you have to make systems that can function even when they're compromised and operate while they're under attack and secure information even though they may be compromised. So I think part of it has to do with recognizing that it's always going to be there. You're never going to eliminate it. How can you set things up in a way where you can survive in that kind of an environment? There are diseases around all the time, and you know, we have immune systems that can sometimes deal with that. Sometimes we get sick and we go to work anyway, and you know, so you have to have a system that's got some degree of resiliency.
I was researching like the band gaps for different semiconductors because I was planning on doing the solar energy band challenge, and I got a lot of different like numbers from different sources. So I was wondering for like finding the band gaps for different semiconductors, which source do you think would be the most reliable?
You mean trying to find the band gaps? There are more already tables available, but some of them you may need to do like more theoretical calculation and all those things. So if you send me an email, maybe we can definitely help you with that.
Is it possible to create the nuclear fusion of elements with laser beams?
That's actually a project called NIF in California, and that's what they're working on. It's called inertial confinement, and I'm not too familiar with that, but yes, that's what they're working on.
Hasn't been successful so far.
Right.
It was supposed to happen in 2012, and it's 2015. So they're under a lot of pressure, not just of the inertial kind at the moment.
They need the pressure.
My second question has to do with the distribution of clean water. There are two fundamental approaches from what I've seen. One, you have a series of factory village, and you have a very large water filtration for the entire village. It's more expensive, and something goes wrong, it's expensive to fix, but it could be more cost efficient. Or you have lots of small devices in each person's home for each person to have, and it's cheaper. What do you think are some of the benefits and problems with each approach?
Well, first of all, those large water systems, you're right, they are very expensive, often funded by large organizations like the World Bank. And what we've discovered is a lot of those large systems are also privatized. They're owned by private companies. And so these villages will often be charged to have access to drinking water. The UN's definition of poverty is having to walk more than a mile for your clean water resources. And so there's been a very large push to actually try these systems that are much, much smaller, that are, for example, pumping systems that don't require electric energy. They require, you know, somebody, I saw one that was really interesting. It was people were sort of doing this merry-go-round thing where they were having these little bicycle pumps where they would get on it and ride it, and they could pump their water instead of having to pay for the electricity to pump the water. They could pump it themselves. Those are far more sustainable and less expensive options. But the problem is, organizations with money like to fund these big projects like dam projects and bigger projects because they get a little bit more bang for their buck. It's hard to go into these little communities, one community at a time, and set up all of these smaller systems. So it's kind of a conflict between how you get your money and where the money is available and what the money wants to be put to, and actually the needs of individual, very small communities. So we're a very big supporter of a public water system. There are private water systems in the state. Chattanooga's drinking water is a private system. It's owned by American Water Company, which I believe is a subsidiary of Veolia. And there have been cases in the states where private water companies have caused a lot of problems. They fire off all their knowledgeable employees, they scale back staff, and then one day you go to your tap, turn it on, and you get air. So we're very much a proponent of a public system, and the smaller systems in developing countries, if those are feasible, we would certainly support that. It's an excellent question, thank you.
Yeah, I think partly it depends on the structure of the society, because if you just put on an engineer's hat and say what's the cheapest per gallon, that goes to a bigger system. And that's correct. The cheapest per gallon is to get scale, do it in large quantities, it's more efficient. So if you have a society that can support that, that's the optimal way to do it. If you don't have a society that can support things at scale because it doesn't have the access to energy, it doesn't have the kind of commercial infrastructure and all that sort of thing, then it's no good being theoretically cheaper if it doesn't work. And so you need a solution that's engineered to the particular needs of the society. So if you go to the Middle East, where they've got a big water problem, but in some cases a lot of wealth, you know, they work at scale. So they build huge desalination plants. And that works for them. They've got lots of oil and natural gas, so they can pay for it. The oil and natural gas gives them energy that they can use to purify seawater, and that's the most efficient way for them to get water. And you know, go to an impoverished African country, and that's not going to be a workable solution. So you know, this is maybe part of the challenge, is that you need multiple different solutions.
Okay, is there any way to use hydraulic fracturing with reduced pollutants seeping into the water? You mentioned something about casing standard.
Yeah.
So hydrofracking in Tennessee is different than hydrofracking on the Marcellus Shale, at least in a large, for the larger companies. What we do in Tennessee is something called nitrogen fracking, where they use nitrogen gas to provide the pressure needed to push the gas out. So there's not a lot of research on nitrogen fracking. We called the EPA and asked them what they had on it, and they said it's such a new process that we're not really sure. We sent community organizers up into the gaslands in Tennessee to find out if people are concerned about their wells or if they've noticed any problems, and we really haven't seen a lot of problems from nitrogen fracking. So the good news about nitrogen fracking is it doesn't use the quantities of surface water that conventional hydrofracking would use. So that's a good thing. We had big concerns when Atlas Energy started buying up leases in the Sequatchie Valley that they would drain all the surface waters in order to do these test wells. But they've assured us that they're only going to do nitrogen fracking. So that's good. They still, however, have to use chemicals and additives in order to keep the fissures open and to encourage the gas to come out. They have these lubricants, and all of these chemicals are considered proprietary knowledge. They don't want people to know their chemical combinations because they've figured out, you know, how to optimize all these chemicals. And so those chemicals get stuffed down these wells and they don't come back up. So we don't know the volume of these chemicals that they're putting down there because, again, it's a disclosure issue, and our state decided not to pass any regulations requiring disclosure until after the fact. However, after the fact, it's a little late if you're one of the people who's had your well damaged. So I'd say, in general, that nitrogen fracking is probably a lot better than conventional hydrofracking. And yet, we still don't know what the outcome is going to be. What I will tell you, for those of you that saw Gasland, there was that dramatic scene where he sets the tap water on fire. We've also found out that drilling drinking wells can do the same thing. And the casing standard is the standard in which they case the line that they drill down. They put in the cement casing to protect the water table. And without a casing standard, they can just pour in a low-grade cement. There's no requiring to testing that the casing is secure. There's no requirement for the type of cement. It's a very loose requirement in fracking. There is no requirement in the drinking water regulations. So that's a problem. We have noticed that some drinking wells will hit a methane pocket and then they'll have methane going into the creek and going into their drinking water. So casing standards was the big thing we pushed, and we didn't get that. But that would go a long way towards making sure that the water table is protected.
So I was wondering, in nuclear fusion, is there any issue about controlling it, like in fission, where you have to slow down the process and get the energy out of it, or you would have to control the energy so that it does not happen too fast and cause meltdown? Is there an issue like that in fusion, or no?
That's actually one of the great benefits of fusion, is there's no possible way to have a meltdown. because you have so little density and you have so little fuel actually in the vessel that when it hits the wall, it immediately cools down. You can have some damage of the vessel wall, but there's no way for a runaway or meltdown.
I've heard that you place a series of solar panels or just one large solar panel in the Sahara Desert, roughly the size of Connecticut. It can possibly generate enough power to electrify all of Europe, but the sources of the term aren't entirely reliable. So I was wondering, is that true?
There's been a proposal called Desert Tech to do that. So the idea is you sort of cover northern Africa with solar panels and then run transmission lines under the Mediterranean to Europe. As long as the cost of solar is where it is, that's probably not going to make a lot of sense because it's a pretty expensive form of solar because of the transmission distances and so forth. And the other problem is the intermittency, the fact that it's only making power when the sun is shining, so you still need power at night and so forth. But as the cost of solar comes down, you know, in the way that you saw in the graphs that were shown, then that may become more attractive, but you'll also have to solve the transmission problem, and that gets into the things that you heard about in terms of power electronics. You know, how do you convert from low voltage DC power to something that you can transmit without major losses? Because if you have big transmission losses, you just gave away your cost benefit. But you know, there's a great solar resource. One of the challenges in Europe is that you've got lots of population density and lots of clouds, and you know, the weather's not great and so forth. In the US, we've got Arizona, so we're in a little bit better shape from that point of view. And so when the Europeans look at the solar resource map, they see northern Africa is much better situated because there's a lot less water vapor in the air and less clouds and so forth. And that's why people have looked at that kind of option, but it's not financeable at the moment because of the cost barriers.
I would add one more, like government has to subsidize too. So it's not just the efficiency and the solar cell cost. So government needs to come in, then possibly you can bring down the cost.
So it seems we have 5 more questions lined up. So I already got the waving sign. We kind of run out of time.
I think the panel's going to stay afterwards. So if you have specific questions to ask them, I'm sure they'd be willing to answer after we let
So let's do the 5 that are in the queue, and then the ones who have specific questions can come up. The panel will stay, and the ones who want to go outside and do the activities can do that. So.
Okay, I have 2 kind of related solar questions. Of the different types of materials, it says the efficiencies, but are there differences in how long they last? Like, do some of them wear out faster? And you mentioned that cadmium might be a good one, but it's toxic. Are there other hazards to having large-scale quantity of the existing type of solar panels, either in the materials themselves or in the manufacturing to create them?
Yeah, as you saw, like different materials, like there are alternate materials known, like cadmium telluride, you can replace it with copper, zinc, containing like more efficient material, but those efficiencies are really low, so still in the 8 to 10% region. So what we need is high efficiency and the low cost materials, and we do have different options. So like silicon is mostly you need single crystals, or if you have polycrystalline or amorphous, so you have reduced efficiency because of the defects. But cadmium telluride and copper indium gallium selenides, we use thin film. So when you use thin film, like we did some research last few years at Oak Ridge, flexible thin film platforms. So can you grow highly crystalline like silicon material or other materials on a low-cost roll-to-roll processing or a template, which we developed for superconductivity? Can we use those technology for this? So these are some of the grand challenges we have, and we are still looking at it. So it's possible to get other materials. So mainly, then again, the band gap is a big issue. So if you have one material, you are going to target only one type of solar spectrum. So since we have the solar spectrum covering from the infrared visible to UV region. So you need a multiple junction solar cell so that you can target the different band gaps, like some in the visible region, some UVs, some in the infrared, so that you can get higher efficiency and higher. So like gallium arsenide and some other 3-5 semiconductors, people have shown like high efficiency, like 45% and small in a laboratory scale. So that's something we need to work on.
The other question was about how long they last, and it depends on the technology that's used. So you saw the vast majority of installed solar now is silicon-based. Most of that is financed on the assumption of a 20-year lifetime. There's no particular reason that you're limited to 20 years. I mean, if you take good care of it. Of course, if there's a hurricane, you could lose the whole thing. Some of the technologies that are interesting because they could be much lower cost, like the organics, it's the lifetime that's the big issue. So yes, you can produce them really cheaply, but they're not very robust because actually the ultraviolet part of the radiation spectrum breaks them down over time, and so they don't have that 20-year lifetime that's built into the model. So it does vary with the material, and it's a big factor in the economics because the way that solar works is you pay all the money up front, and your fuel is free because it's just the sunlight. And so they have to last long enough that the electricity you generate over that lifetime pays back the initial upfront investment plus interest. And so there's this trade-off of lower cost material, lower lifetime, that is one of the challenges that has to be overcome.
I'm curious about hydrofracking. You mentioned that nitrogen fracking was being used in preference over other kinds of fracking because they have a tendency to release pollutants into the water table. But what I'm wondering is there a possibility that the nitrogen, if it's not in an inert form, could cause an algal bloom? Has there been any speculation about that?
Excellent question. The oil and gas industries are not doing nitrogen fracking because they feel like hydrofracking is causing a lot of pollution. It turns out that the shale play that they are going after, the Chattanooga Shale, is quite fragile. And in 2010, Atlas Energy fracked a test well and used 417,000 gallons and crushed the play, completely ruining it for any kind of gas extraction for themselves or for anyone else. And so they came back to the drawing table and said, we need to find another way to do this because that play is way too fragile to use water. And so they came up with using nitrogen. And the nitrogen, they have told us, is an inert gas. We did worry about algal blooms. It's been quite popular on the news lately. EPA said it's becoming one of the top 3 pollutants, is that nitrogen pollution and algal blooms are quite toxic. So that was the first thing we asked was, what's the form of nitrogen and are we going to have a problem with algal blooms? But the nitrogen would be injected many thousands of feet underground, and since it's really, the recovery is not the same as there's actually no recovery. They shoot it down, it's inert, and it goes away, so there's no recovery. The only thing that we're concerned about is that there's also no recovery of the chemicals. So the chemicals are still down there, possibly interacting with the groundwater. We don't know what those chemicals are, so that's still the unknown.
I was wondering about the urban infrastructure. I had 2 ideas. One was over autopilot for cars, and one was more like train-based. And I was wondering what to focus on more. Like there's a political side to it, and the locomotive side, and all of the systems that are involved. And I feel like I could write 5 pages on each of them. So. Which one should I go for more?
Don't tell me.
I don't think there is a single solution. It is what you want to achieve in the end in terms of sustainable development and how you want the community to be developed over the next. Because these things are not something that you can implement, in just a a few months. It takes time, and it depends on the density, it depends on the activities, it is dependent on the sustainability goals that you might have, on how you want to develop the community, as well as, of course, the cost benefit associated with it, because it has to be economically feasible. So the thing to do is to look at all the solutions that are available, what would benefit, and how you want to develop that specific community as a whole. So you have to look at and therefore decide on how you want to put processes in place, as well as put strategies in place to develop different kinds of things. The key should be mobility, accessibility, and economic development, and sustainability. That is, you do want to increase. So, if you start taking these goals, that objectives that you want to meet, and then start designing the approach you want to take. Each has its own, what I would call it, benefits, as well as, deficiencies in terms of either cost or infrastructure or investment that might be required. And so you have to take it accordingly. That is, for a small, low-dense population, you might have more personal transportation requirements, but for a high density. But at the same time, we want to develop a community that is mixed use versus something that will, produce urban sprawl, right? I mean, put people in different places that will increase how much they travel, and therefore increase the pollution and those kinds of things, emission. So what you want to do is look at those aspects that you're interested in, and then try to create a solution by bringing in these various, what I would call it, options that you have, whether it is personal transport versus public versus, paratransit, that is, or transit on demand, and different kind of creative solution. This is where it becomes a challenging issues, and then how do you develop the infrastructure associated with it, because you want to have free flow from one mode to another mode, however you build it, right? I hope.
I was curious then if you could have an enzyme or a other sort of organism, or a microorganism, like say bacteria. Could they be modified to where they could absorb these dangerous materials like salts or heavy metals from water to basically clear those materials out of the water?
Oh, septic tank.
Yes.
You said with the EATR project that they're trying to optimize the plasma, but the more energy you try to get out of something, the more energy you have to put into it. So what necessarily gives them the reason to believe that they're not getting more energy out of it than what's put into it?
For this experiment, they can actually heat the plasma to the temperature it needs for the fusion process. They can also use tritium. So right now, all the experiments in the US and around the world use deuterium. So you actually need deuterium plus tritium to release the energy and create the helium and the neutron. So that's what they're going to be able to do there. So that's how they're going to get a lot of power out.
My question had to deal with the enhanced virtual reality. We already have a form or so of virtual reality. You've got your full feedback system, so to speak. You've got the Google Glass being developed. What exactly does this entail?
So really, virtual reality for the purposes of this tool for exploring science. Imagine that you could get a bacteria that you're trying to model and you're trying to look at it at the atomic level. Virtual reality would let you look at your scientific data in a way that you're not able to look at it just by looking at sheets of zeros and ones. But if you can make a picture that's compelling and you can manipulate it in 3D, you can really analyze your data and come up with the knowledge you're looking for by using virtual realities. A picture is worth 1,000 words, so a 3D picture is worth 40,000 words. If you can manipulate it and see your data in different ways, maybe it says 100,000 words.
Okay, so I'm going to to end the official part here, let's thank the panel one more time.